Hello, everyone. Anybody have any questions before we get started?
Yeah, just a logistics question about this
Okay.
upcoming test. So our practice test is open in Canvas right now,
Right.
but the actual test itself has not been up there. Was there? Did I misunderstand that? But I thought that there
No,
was
I thought I'd put it
supposed
up the other day, but I discovered this morning with my day class that evidently the same thing happened. I didn't put it in the module. They had actually found it by going to the grade book and then clicking on that grade.
Gotcha.
I don't even think y'all were able to do that with the way I'd forgotten to do what I forgot to do. But I just took the module from my day class
Mhm.
and copied it into this class.
Okay.
So you should be able to access it. Let me see. I'm going to put it up there right now. I'm going to go with quiz. I'm talking to myself just because that helps me go through this. So anyways, test 2, chapter 3 and 4. And what I did because of that screw up is I decided to go ahead and make that not due until the 20th. So your next
perfect.
homework
Okay,
sets will
good.
be due on the 19th. That's the normal Sunday. But since we have the 20th off, I figured I'd give you the day to do the up to 3 attempts on your test 3.
Thank you, because we were all concerned that we would have like a good maybe 12 hours to take this test, maybe. So
Yeah, you got plenty of time. Sorry about that, everybody.
Okay, thank you.
No problem. And I've now moved chapter 5 homework and conceptual homework to the week 4, June 13th and 19th module. I did add 4 links to examples in my YouTube channel. There's other stuff in there as well. Oh, it looks like I got 2 sets of those, so I don't like where those are, so I'm going to remove these.
So, I mean, the practice test is.
What's that? I heard something about breakfast, and I don't know how. I'm pretty sure I didn't hear breakfast, but still.
Sorry. Does that mean that the practice test is also going to be extended since the test will be extended?
Yes, exactly.
Okay. Thank you.
So I did that in the other class. I don't think I've done that here yet, but I will make sure I do it. Oh yeah, that's right. I forgot your class has the practice test and a practice test module, doesn't it? Oh, actually, no, I brought it down. Okay, so let me fix that. Your online tests are evidently in the online test area. They had been, but I'm now putting them back in the module. So yes, this practice test 2 is going to be available until the 20th at 11:59 p.m. And it's due at 11:59 p.m. Save. Okay, now I got that. Any other awesome questions you cats got? Now I got this really fancy paperweight here. See, this is nice. Ooh. Okay, so evidently I left it on since Thursday, and it died, and it's like less than 1%. And I discovered that my iPad used a very special cord where this end like plugs into an iPhone, but doesn't plug into the iPad, and this end is not a USB, but it actually plugs into the iPad. So I've literally got like no way to charge it except for the very special little charging block that I happen to already be using on something else. So I couldn't get it charged in time. What I decided to do is I moved that little camera that I use over there at my other office. I decided to move that here in hopes that will still look a little better, but I'll go back to the iPad next time. So I apologize if it doesn't turn out as clear. Here's what it looks like. Let's see. Oh, it looks great, doesn't it? Nice focus and everything. I feel good. Is that actually seeable, viewable, and whatnot?
Yeah, it looks all right, but when you start writing, it might be different.
Yeah, I'm gonna have to. I'll try to write bigger. Maybe that'll help, and I'll try to write more legibly. But we're gonna work through it. I apologize for not having this charged. I will definitely have it charged by next time. The good news is we've got a couple examples that I want to work on here, and they're sort of similar to the ones in the book. So if you miss anything, it's not gonna hurt you. In fact, it's essentially the same as the book. I might have changed a little bit about what we're asking about though. So last time we had finished by doing an Atwood machine. I solved for the tension as well as for the acceleration of the Atwood machine. Remember, Atwood machine is just basically a pulley applied to basically two masses where one's heavier than the other. And I use just generic forms, M1 and M2 are big M and little m to suggest, the big M is the bigger of the masses, and solve that using Newton's second law. So the big deal is using a free body diagram. So the first thing you got to do when you get a problem with Newton's second law is you need to draw a diagram, and then you need to sort of trim that down to a free body diagram in which the object becomes a particle, usually at the origin, and then you have all the forces laid on it in the directions that they point, and then you break those forces up into components in the x and y direction. Then you use the summation of forces in the I direction equals mass, or excuse me, in the x direction equals mass times acceleration in the x direction. Summation of forces in the y direction equals mass times acceleration in the y direction, and even the z direction if you want. So that's the big process that you got to go through with Newton's second law. And you saw that when we were, whoa. It's got the video set backwards. This is not cool. Nope, that's not it. That's not it. Well, I gotta figure out. Y'all can read backwards all day, right? Today
is it backwards for the recording or for us? Because for us, it's
looks
fine.
good. Okay, cool.
Yeah.
That's just it must be well, it's showing on my side backwards, which is not helpful to me at all, but luckily I don't feel that way. Let's see if I can do something. Video settings, let's see. Original ratio, touch up appearance. I know there's a way I can. Let's do advanced. Oh, mirror my video. That's what I want to do. I want to take it off of mirror my video. There you go. Now y'all still see it forward, right? Y'all probably didn't see any change happen just then. Okay, cool. Well, my crap was backwards and I couldn't read a thing. Okay. All right. So what I said was you got to use summation forces in the x direction equals mass times acceleration in the x direction. Summation of forces in the y direction is equal to mass times acceleration in the y direction, and maybe even summation of the forces in the z direction is equal to mass times acceleration in the z direction. And when you're using those, the only thing that makes them a vector is a plus or minus symbol. So that all depends on what direction you choose your coordinate axes pointing. And if a vector has a component that's pointing in the positive direction, it'll be written as a positive number. And any vectors written pointing in the negative direction will be written as minus that symbol. Okay. Not only that, we also learned that you can do a free body diagram. And you could do a free body diagram for each object. And that's sort of the stuff that you need to do. If you are wise enough to go ahead and make your coordinates consistent from one of those bodies to the other, then that'll save you a lot of headache as well. So for instance, when I did the Atwood machine, I decided the left-hand side was going down because that was the side that had the big mass on it. So I made like the positive x-axis point down on the left. To make that consistent, I made the positive x-axis point up on the right. Otherwise, I would have to have something like acceleration of the left equals negative acceleration of the right or something weird like that. So let's start off with a problem that's not unlike the one your book has, but I'm going to say which direction if at all, will the block on the incline accelerate? So that's just a question. Now I'm going to draw the diagram. And of course, if you were doing this problem for real, you'd actually have the diagram given to you unless I described it. So let's say the diagram looks like this. I've got an inclined plane. The angle is theta equals about 37.0 degrees. Okay. And I have attached to it a little pulley that's massless and frictionless. A string comes off of this parallel to the incline, and the mass of this guy is going to be 50.0 kilograms, which I'm going to call M1. And the mass of this one is going to be 40.0 kilograms, and I'm going to call that M2. I'm going to say this surface has a static coefficient of friction equal to 0.40 and a kinetic equal to 0.20. So you haven't heard anything about those yet, but now I'm going to give you an idea of what friction is. So let me kill this view for a second. What I want you to think about, and you can actually do this yourself on your desk if you have access to something like a calculator that has these little rubber nipples, that works really well. If you have something even heavier, that works even better. But if you set it on the surface of a desk or something, and you slowly, attentively pay attention to how much force you're applying to it, what you'll see is you can put a light force on it, a little bit heavier, and keep on going. And then eventually what will happen is you reach a large enough force where it takes off, and then you feel your finger get sort of less stressed. In other words, there's automatically the force that you have to apply to the calculator to keep it moving is very, very small. And the reason that is because it turns out if you take the friction force and make a plot of it versus the applied force, this is the symbol I use for friction force. I'm going to show it to you in a second. And I use a script F for it. So back to this. If you make a graph of the friction force versus the applied force, see that? Notice that little script F right there? That's the symbol I use for friction. What that information that I just told you says is basically that the friction force matches the applied force exactly until it gets to some critical value. Then it drops down to a static force like that. Okay. This particular value is the same as this particular value, and it's mu static times the normal force. So that's part of the reason we've been learning about normal forces at all, is because the normal force is what the friction force is proportional to. And this force right here is mu kinetic times F normal. But it's a little odder than that, and specifically because you got to account for this friction force not being that big all the time. Because if this was the whole friction force, then this would just show that friction force horizontally, and then it would drop down like that. But notice the friction force just matched the applied force at every point. So in fact, the formula is static friction is less than or equal to mu static times F normal, and kinetic friction is equal to mu kinetic times F normal. Okay, so that's the information you didn't necessarily have yet. Can y'all see that? Is that, I mean, I know I didn't write as big as I intended to, but I think you can see it. Did everybody get that picture and everything? Your book has a table. I think it's on page 130, maybe somewhere around there. It's like the second page of the chapter. It has a list of coefficients of friction, and there's a very specific experiment that you can do to determine them. but it gives you friction like rubber on dry cement versus rubber on wet cement versus rubber on any surface, ice on ice or steel on ice, all sorts of stuff like that. But the big thing that you see is the normal force, or excuse me, the static friction force, which is the S there. That's the friction when the object's not moving. That's why I call it static. That force is always larger, and therefore that kinetic friction is coefficient is always larger than the static friction coefficient is always larger than the kinetic friction coefficient. Okay, that's actually why we turn into a curve when you're actually going around a curve in the winter and your back end starts to slip out from behind you because it's iced over. They tell you to turn into the slide. Well, that's why, is because the reason that your car grips so well is normally it's having kinetic or static friction between it and the tires. But when it starts to spin out, the tires are not parallel to the way they're going anymore. So it can't be anything but kinetic friction. So if you're early enough to turn the wheels in the right direction, you can sort of get your wheels and tires lined up in the direction you're going and recover static friction. Okay. So now what we're going to do is try to figure out which way does it accelerate. And then I might even add to it and say, now that we know it accelerates a certain direction, what is the acceleration? Okay. So let's do it this way. First off, I'm going to consider, so solution. Assume block slides up the incline. Now, why I had to do that is, remember, friction tends to impede motion. So if the block's going up the incline, then that means the friction force is going to be pulling it down. However, if the block is going down the incline, then the friction force is going to go that way. So I've got to consider it in a couple different scenarios. So now I'm going to draw my free body diagram. I'll first draw it for this one. I'm going to say this is my positive direction. This is my mass M2. And I'll draw the forces acting on it. The forces acting on it are going to be the weight, which is M2 times G. That's in the positive direction. And the tension, which clearly that pin is dead. The tension T, which is in the negative direction. So this particular free body diagram gives me M2G minus T is equal to M2A. I'm going to call that equation 1. Now I'm going to do something a little tricky. We haven't done this before, but it's pretty normal with the inclined plane. Sometimes you'll see, like in another example we'll do today, we're not going to have this tricky coordinate system, but in this time we are. What I'm going to do is draw the positive x-axis, because I want it consistent with this side. I want going up the incline to be positive because that's the same way as it's going down. And then I'm going to say that's my positive y-axis, like that. And in fact, this thing's tilted at an angle of theta. Okay. Now here, I am going to have a force, or excuse me, a mass, M1. It's going to have acting on it gravity, which is M1 times G. But it's also going to have acting on it a normal force, F normal, acting in the positive direction. And since we're pretending the block is going up, we're going to assume the friction is going that way. So we also have a positive tension going this way. And we have a negative friction going this way. And that's F sub S, meaning F static. Okay. Now, we've got free body diagrams. I've even color coded them to help me remember what's black or what's positive and what's negative. But one of these vectors is not in component form, so I can't use it yet. What I realize is if I want to go from the tail of the vector, which is right there, to the head of the vector, if I first go along the y-axis, I'm going in the negative direction. And if I'm going in the x direction, I'm going to have to go this way, which is the positive direction. Okay. Now, here's some geometry that you should know. If you look at this shape right here, y'all see that's a right triangle, right? Where this is a 90-degree angle. So if this is, say, 30 degrees, what would this one be?
60.
60, exactly. It's a complementary angle because they add up to give you 90. So this is what we call 90 minus theta. But from here to here is a 90-degree angle as well, right? Here to here. So these two are complementary as well. So that tells us this is actually theta right there. That's a key thing that you're going to have to do repeatedly this semester and next. Okay. Now you see that in fact, this side, the red side, is actually touching the angle theta. So that's adjacent. So that tells me immediately that this side is M1G cosine theta. And this one is M1G sine theta. Okay. So if I take the summation forces in the y direction equals mass times acceleration in the y direction, what I get is F normal minus M1G cosine theta is equal to 0. And that's because we're assuming the block's not going to be like bouncing up and down or anything like that, right? It might actually accelerate up the incline or down the incline, but the key point is it's probably not going to bounce around like that. So yeah, that acceleration should be 0. And that gives us another useful expression that the normal force is actually equal to M1G cosine theta. That's going to be equation 2. Now, I want to do a little bit of thinking about this right now. Notice the graph of cosine from 0 to 90 is just this part to the left of that mark, right? So you see cosine's a maximum when theta equals 0 degrees. What that means is a flat roof has to supply a buttload of normal force. In other words, if a flat roof weighs 100 pounds per square foot, then it's going to have to absorb that whole 100 pounds just for its weight. And if you stand on it, it's going to take that weight too. And if you put snow on it, it's going to take that weight too. But as the angle gets larger and larger, the normal force that the roof has to supply gets smaller and smaller. And that's why you see, for instance, ski cabins and stuff like that normally have a steep pitch roof. Or the house on The Shining, for instance, had a pretty steep pitch roof. And that's because the mg cosine theta gets small. And you know, winter snow prone areas, they have to carry a lot of snow sometimes for months on end. So it's better to put a steep angle. On the flip side, in the Outer Banks, when you have high winds, high pitch roof can actually decrease the pressure on the top, and that'll suck the roof off. So we actually shoot for almost flat roofs on the Outer Banks, specifically to save us from hurricanes, because that's our major thing. All right, so there's a little analysis of that. Now I'm going to do a summation of forces in the x direction.
I have a question.
Yes.
So we set the summation of forces in the y direction equal to 0 because it's accelerating in the x direction, not the y direction.
Yeah, there's no acceleration in the y direction.
Okay, that's where we can set it equal to 0 and then solve for the normal force in this problem.
Yes.
Okay. All right.
Okay.
Thank you.
So now I'm going to say, okay, well, the force is acting in the positive direction is really only T. So I'm going to say T minus M1G sine theta minus the friction force. That's got to equal M1 1 times A. Now I don't need to subscript A because we're assuming the rope is not stretching, nor is it getting slack. If it's stretched, then you could say mass M1 moved for a split second faster than M2 or something like that. If it got loose, you could say mass M2 moved a little, or mass M1 moved a little faster than M2 for a brief period. We're assuming that it stays taut and that it doesn't stretch. So now, if we want to see which way it's going to go, what we're going to do is try to see, does this friction force, is that, well, when I do this whole left side, for instance, is that whole left side going to turn out to be negative? Because if it is, then that means the acceleration is going to be negative, which is in contradiction to what we were assuming. And in fact, the friction is too large for it to go up the incline. Now, what we could do is consider the largest factor of the normal, the friction force could be, and that's when it's mu s times normal force. So I will do that. So assume friction force, or excuse me, let's assume, well, that didn't erase very well. Let's assume the friction force equals friction force max, which is mu s times the normal force. Okay. So now I've got, this will be equation 3, by the way. So I've got M2G minus T equals M2A. That was equation 1. I've got equation 2, which is T minus M1G sine theta minus mu static times, using equation 2, M1G cosine theta. Now I've got that and that's equal to M1A. So I'm going to add the two equations. You see that the tensions cancel out. I end up getting M2G minus M1G minus mu static times M1, mu, this is times sine theta, I left that off, minus M1G cosine theta is equal to M1 plus M2 times A. So I can now put in numbers and start making some sense of it. So let's calculate the left-hand side. So I'm just calculating now the left-hand side of that equation. So M2G, we said M2 was in fact 40. So that's going to be 40.0 kilograms times, actually, let's divide through by G. So I'm going to divide through by G. So this will be dot, 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 and this will be over G. That way I ain't got to do more math than I want to. Okay. So I now have 40 kilograms minus 50.0 kilograms times the sine of 37 degrees, which you guys remember, 37 is one of those special angles. It's the 3, 4, 5 triangle, and it's the smaller angle. The other one's 53, right? So it's opposite the small side, which would be 3, and then it's adjacent, or its hypotenuse has to be 5. So this is going to be 3/5. So this whole thing right here just turns out to be 30.0 kilograms. Now this next one is minus 0.40. That's the coefficient of static friction, which is right there, times the M1, which is the 50. Kilograms, and times the cosine 37 degrees. And that one's, of course, 4/5. So this becomes basically 16.0 newtons. And this is all equal to M1 plus M2 times A over G. So I've got 40 minus 30 minus 16. So that becomes negative. left-hand side is less than 0, that means friction is too large for box to slide up. Does everybody understand why that's the case? If it's negative, then this side has to be negative, which means the acceleration is in the negative direction, which means it's going down. Okay. And the reason it's going down is, one, it's got this force pointing down, and this force you can't get rid of. It's just got to be the parallel component of weight. But this force with this force makes it too big for the tension to pull up. Therefore, this scenario of us assuming it'll go up the incline is completely wrong. Now we got to try the other way, which is assume the block slides down the incline. In that case, the friction is going to be over here and pointing that way. Any questions on that? So the equation 1 and equations 2 still are the same. So now assume box slides down. So we still have equation 1, which was m2g minus t is equal to m2a. We still have equation 2, which is F normal is equal to m1g cosine theta. And the only thing that really changes is now this static force is actually pushing up, because if the box is sliding down, the static friction is trying to slow it down. So let's call this 3 prime, since the other one was called 3. I'm going to say 3 prime is now T, because for this part, Fs is going to point that way. So you can see that's why I put that. Okay. So now I'm going to say the friction force is down, or excuse me, is up the incline. So I'll say plus mu static. We're going ahead and considering the largest possible scenario times the normal force, which is m1g cosine theta, minus m1g sine theta. That takes care of that. Is equal to m1 times a. So now I'm going to add that with minus t plus m2g is equal to m2a. And in this case, notice the tensions cancel out again. I get mu s m1 g cosine theta minus m1g sine theta is equal to m1 plus m2 times a. Now, again, to get rid of the g, I can just divide both sides by g and put it over here. And now I'm going to calculate the left-hand side. Now, we're assuming the acceleration is going downward for this one, right? So the acceleration better come out to be negative. So in other words, if I get this being positive, then I know it's not going to move at all, because in order for it to do that, the static friction would have had to supply a larger force than just the applied force, because the applied force is just m1 g sine theta. So the left-hand side gives me 0.40 times m1, which of course is the 50.0 kilograms, times the cosine of 37 degrees. So we already know cosine is 4/5. So this is going to be 16.0 newtons. Because 4/5 times 50 gives me 40. 40 times 0.4 is 4 times 4, which is 16. And then I got minus 50 kilograms times 3/5. And that gives me 30. Okay. So in fact, in this case, we see that the static friction force is actually not smaller. We end up getting a negative, which is exactly what we expect. So the actual acceleration will be in the negative direction. So we get 16 minus 30 would be negative 14 kilograms is equal to 40 plus 50 is 90.0 kilograms times A over G. So finally, I can go ahead and say this implies that A is equal to, I'm going to divide both sides by 90. So I do 14, which is negative, of course, divided by 90. That gives me 0.155. And then I multiply that by 9.8. And that gives me negative 1.52. So A is equal to negative 1.52 meters per second every second. So it is actually going down. Any questions on that one? I'm probably going to recap, show you everything we did just to make it a little clearer to you. All right, so what we had was this problem. It says, which direction, if at all, will the block on the incline accelerate? So what we realize here is by having a static coefficient of friction, the 40 kilograms might be enough to pull the 50 kilograms up there, but the friction might just be big enough to stop it. Or the 50 kilograms might be big enough to pull this one up, but the coefficient of friction, the static friction force, may actually be large enough to keep it from moving. So what we tried to do is figure out which one of those scenarios is real. So I first assumed the block was sliding up the incline, which would be the acceleration. Notice I called that the positive direction, which would be a positive acceleration. So I set up all the equations as if the friction force was this red one. The next part, I'll assume it's this green one. So the summation of forces in the y direction or in the x direction for this guy was just positive, was pointing down. So I did m2g minus t is equal to m2a. That's just for the hanging mass. For the mass on the incline, the summation of forces in the y direction was the normal force pointing up minus m1g cosine theta. And we didn't expect the block to bounce up and down or to jump off the surface or dig into the surface. So the acceleration in the y direction should have been 0. That's why we put 0 there. So that allowed us to determine the normal force for both parts. Whether we're assuming the block's going up the incline or down the incline, the normal force is going to be the same. The part that is going to be different is which direction the friction force points. So in this first part, we're assuming since the block's going up the incline, the friction force is going to try to slow it down or try to prevent it from moving since it's static. So that would actually point in the negative direction. So I get T minus M1G sine theta. That's just the component of weight parallel to the incline. And that also makes its appearance, I think, in the first episode of Big Bang Theory. So if you want to watch that, they're trying to bring some furniture up steps. But anyways, T minus M1G sine theta, that's actually tending to pull it down. And then minus the static friction force, which is intending to slow it down, is equal to M1A. So if I assume that the static friction force can be as large as it can be, Then I'm going to use Fs is equal to mu s times F normal. I plug that in, I get T minus M1G sine theta minus mu s M1G cosine theta equals M1A. I add those two equations because the negative T and the positive T will cancel each other out. And I get M2G minus M1G sine theta minus mu s M1G cosine theta is equal to M1 plus M2 in parentheses times A. Well, I don't like doing that extra calculation of 9.8. So I divided both sides of the equation by G. That made this side A over G, and it made me only have masses and coefficients of friction over here. So I knew that M2 was in fact 40 kilograms. And then M1 was 50 kilograms, but sine of 37 was 3/5. So that gave me 30 kilograms for this total. And then mu s was 0.4, M1 was 50, and then cosine was 4/5. So 4/5 of 50 would be 40 multiplied by 4/10 would be 4 multiplied by 4, which is 16. So I basically got 40 minus 30 minus 16, that'd be negative 46. So I got a negative left-hand side, which is actually, for starters, is a contradiction because I said it was going up the incline, and that's the positive x direction. So really what's happened is the acceleration turned out to be negative because the friction force was big enough to cancel out the attempted motion in the up direction. That friction force, remember that static friction force only goes up to 0.4 times the normal force. So since the only force would have been 40 minus 30, that had been 10, it would have only went up to 10 and there'd be no acceleration at all. So that's how we figured out it's not going up the incline. Now I got to consider, what about if it was sliding down the incline? Well, the equation 1 and equation 2 don't change, and the only thing that changed about equation 3 is now this static coefficient or the static friction force is pointing in the up direction. So I just made that equation T plus mu s M1G cosine theta minus M1G sine theta equals M1A. And then I add it to the original equation 1. And what it worked out to was giving me, in fact, a negative number, which is exactly what we expected for the acceleration of the mass going down the incline, because down directions in the negative x direction. So that gave us what we expected. So it clearly is moving downward. Now all I have to do is divide both sides by 90 and then multiply both sides by G. That's what I did. And I got negative 1.52 meters per second every second in the downward direction. Anyone have any questions on that? Okay, so I hope that was fairly clear. That is actually one of the harder type problems. Now, when you take your dynamics and your statics classes, they'll actually give you some algorithms that you can use, so you don't have to sort of poke and hope, which is not really poking and hoping as much as I'm using logic and reason to discover a way to figure out which way it goes. Okay, physics is supposed to be more on the discovery side. Engineering is more on the application of what's already been discovered. That doesn't mean engineers don't discover, they discover all the time. It's just you need to learn how to apply the laws of physics as they are. And if there happens to be a missing concept or something in your repertoire, then you're going to have to figure out a way to discover at that point. So like I said, good news is they give you nice little algorithms in your statics and dynamics classes. And here we're just going to try to figure out a way every time. So that was the first problem. And that was actually a tough one, but I wanted to open up with a tough one because I know that's when I have your attention the best. When class first starts, I probably have your best attention span. So now let me give you another problem. This one's going to be a little bit easier. What I'd like to know is at what angle theta will a block of mass M slide down an incline if the static friction is mu s, if the static coefficient of friction okay, everybody read that. I'm curious, is it turning out okay still, or is it looking bad?
It's all right. I can see it pretty well. I don't know about anybody else, but it's not like as blurry as it was.
Awesome, good deal.
I can see it, yeah.
All right, so let me draw a diagram what I'm talking about. So what I have is an incline of angle theta, a mass M. So my free body diagram is going to be this. And I have a normal force acting in the upward direction. And I have a friction force that tends to keep it from going, and that's going to be the static coefficient of friction. So this is F sub S. And in fact, as we saw before, since this angle is theta, this angle is also theta. So this gives me mg cosine theta. And this one's in the positive direction. So that gives me mg sine theta. And I should probably make this a capital M because it looks too small there. Okay. So let's solve our problem. So the summation forces in the y direction is equal to mass times acceleration in the y direction. Again, we're going to assume that acceleration is 0 because we do not expect the mass to be bouncing up and down or digging into the surface. So with that, I want to get Fn minus mg cosine theta is equal to is equal to plane 0. Just telling you that. Oh. Okay, so the normal force is again mg cosine theta. That's going to come in handy. Now, the summation forces in the x direction is equal to mass times acceleration in the x direction, gives me mg sine theta minus the static friction force is equal to m times a. Now, what I wish is that this static friction force is as big as it can be. So let Fs be its maximum. And imagine A being slightly bigger than 0. So just a itty bit bigger than 0. So we're going to assume it's essentially 0. So now what I'm going to say is mg sine theta minus mu s mg cosine theta is equal to 0 at the instant it can accelerate. Does that make sense? So if these are just breaking even, all it takes is a stray molecule bouncing off the back of the mass, and it'll knock it down the incline. So that's what I'm trying to do by setting the mass equal to 0. And I think you can see that what you end up getting is the mg's cancel out, which is nice because this means this is a rule of physics that we're going to get here that's independent of what planet we're on, as long as we have gravity. And it's true for all objects, no matter what their mass. So we end up getting mu sub s is equal to cosine theta over sine theta. Excuse me. No, it's equal to sine theta over cosine theta. Mu sub s. So I pull this over here, it'll be mu sub s cosine theta. And over here will be just sine theta. So mu sub s is sine theta over cosine theta. So we can solve this for theta by realizing that mu sub s is just equal to tangent theta. So theta is equal to the arctan or inverse tangent of mu sub s. So we've just figured out a way to actually determine the coefficient of static friction. You put the object, whatever it's made of. So if you want to do rubber, you put a rubber block, and you want to know what the static friction, the static coefficient of friction is for rubber on wood. Then you make a plank out of wood and you put a rubber block on it, and you raise it up slowly, give it a little tap. If it doesn't slide down, you haven't got it high enough. Give it a little lift higher. Again, tap the incline just a little bit, like that light. If it doesn't slide down, you got to keep going farther, but keep going until you finally just tap it that one time, and then the mass takes off. You take the inverse tangent of that angle, or excuse me, take the tangent of that angle, and you have the coefficient of static friction. So there's two ways you can look at it. You can find the angle, or you can say mu sub s is equal to the tangent of theta. So there's two results we got there. And that's really remarkable, right?
So I have a question. Can we use this fact without having to prove it, or
if I recall, I think they did number it, so that would be normally the case.
Okay.
If it's not numbered, you're not really supposed to.
All right, thanks.
No problem. All right. Any other questions on that or anything else like that? Okay, so this is applying Newton's second law, essentially. And you've seen a couple different ways of doing it. Now we've learned about friction. We've learned about static friction versus kinetic friction. Let me work one more problem to give you an idea of how static and kinetic friction go. So this time, let's see. I'm going to write what force F is required to accelerate the blocks below, and B, if 120% of that force is applied, what would A be equal to? Okay, so now I'm going to draw a diagram. There's a wall. There's a block, 5.00 kilograms. There's another block, 3.00 kilograms. And I'm going to call this MA, and I'll call this MB. And I'm going to connect them with a rope. And the pulley, actually, I'm gonna make the pulley bigger than that. Okay. And I'm going to say mu s is equal to 0.60 and mu kinetic is equal to 0.45. Okay. So you see what's going on. I got a 3 kilogram block sitting on top of a 5 kilogram block. The mu s is for all of them. So that's the friction coefficient for block on block, for block on surface, all of it. Okay. So first, free body diagram for A, I'm going to assume that the object's going to go this way, the top object. So I'm going to draw this as my positive x-axis, and this is my positive y-axis, and I'll say that's a mass MA. Acting on it is a force MA times G. Also acting on it is a force F normal A. And also acting on it is a tension T and a friction force F static. So my y direction gives me one result. Y gives me the FNA is equal to MA times G. That's going to be equation 1. My x direction stuff gives me that T minus FS is equal to MA times A. That's going to be equation 2. Now for the other body, to be consistent with that, I said this going this way was positive. So that means that going that way is positive. So I'm going to make my x-axis this way for this mass. And I'm going to say this is MB. The forces acting on it will be the force F, which is what we applied to it. I didn't even draw it here, but I'm applying the force F here. Okay, not to be confused with this thing. So I have a force F acting in the positive x direction. I also have a F normal B pointing up. But notice the F normal A is the force acting on mass A as a result of mass B. So Newton's third law says the force acting on B as a result of A is the negative of that. So in fact, this becomes F in A this way, but we also have acting MB times G. Now this thing's being pulled this way, so I've got a tension going this way, T. I've also got a friction from A going this way, and I got a friction static going this way. Does that make sense that all those forces are acting on it? Any questions on that?
I have a question, if that's what you just asked. I don't know, you're cutting off on my end. So I was wondering if you could just like quickly go over the forces again.
Okay. So that's fine. That's a good thing to ask. So you've got the force that we're applying, say, to some rope to pull this thing ahead. That's the little F there. Okay. And we're only doing the free body diagram for the 5 kilogram mass right now. We've already done the one for the 3 kilogram mass. So it's going to have a normal force. That's the force this table surface is applying to it. And it's normal to the surface. We also have F equals NA was pointing up on this mass, but according to Newton's third law, F equals NA is the magnitude of the force that the 3 kilogram mass applies to the 5 kilogram mass. So it'll be in the negative direction, F NA. Then we have the object's mass, which is MB, or excuse me, the object's weight, which is M sub B times G, which I realize that's really small. I'm trying to not ship to a separate sheet of paper because it'll be hard and confusing to go back and forth between two pieces. So that's MB times G, that's the weight. Now, also, if you ask this block, it'd say, hey, this dude's pulling me this way with a force F, but this rope back here is slowing me down. So it would feel the tension acting that way. Now, this block is trying to slide this way as well. So that tends to apply a friction force on the block B as a result of block A, which is what I drew there. That's F sub A. So that's the friction force due to A. Okay. And we have the friction force due to B sitting on the ground, which is right here. So I called that just F static. Does that help you?
Yeah, it does. So there's three, I guess, negative forces here. So you've got the tension, the static force of the main block, the 5 kilogram block, and then the friction component from the 3 kilogram block.
Exactly.
Okay, thank you.
No problem. And I'm actually going to move this Y. I'm going to move this Y here. And I'll move this X here just to allow us to use room more efficiently. So what I have here is F in B minus F in A minus MB times G is equal to 0, which I think you can realize means F in B is just going to be MA plus MB times G. Because this comes over here and becomes a positive MBG, and this is already MAG. So when it comes over here, it becomes positive, so I can just factor out the G. So I know that expression now, that's going to be equation 3. And that's what we use to find this friction right here, because it's mu static is the biggest it can be times that normal force. Now in the X direction, we've got F is the only thing acting in the positive direction. We've got minus Fs sub A. And we've got minus the tension. And we got minus Fs sub B. In other words, the friction force due to B. And all that is equal to MB times A. So that's equation 4, actually. I couldn't have made that any uglier. Again, we're assuming that the rope is not stretching or getting loose, so the A should be the same. Now, if I let A go to 0, then I'm finding basically when FSA and FSB are their largest values. And I'm finding out what force will just be large enough. In other words, I have to take a force a little bit larger than that, 1 in the 84th decimal place, say. That force would be just enough beyond what we calculate here to make it actually accelerate. So I'm going to let this go to 0, and 2 is going to become, notice when A goes to 0, T is just equal to mu sub S times MA times G. And 4 becomes F minus mu S MA plus MB times G minus mu S M A G. That's because of that one right there. So I've gotten this term and this term, and now I have this one as well, which is minus mu S M A plus M B times G, and all that's equal to 0. Good God, that was bad. Okay, the main thing that you're trying to see here is this term is just a mu S times the MA times the G that you got there. This term is just the tension, so you get another mu S. That is the actual one, excuse me. This term is the mu S MAG, and then the tension is minus mu S MG. Actually, that was a problem. I mixed them up. When I said this FSA, that's supposed to be the friction force, the static friction force due to A. That should have just been MA times G. Sorry about that. That actually gives me a little bit more room. Thank goodness, right? Okay, let's regroup what we're doing here. So I've got F minus FSA minus T minus FSB, but I'm taking this to go to 0. So this side's going to be 0. So I pull all this junk over on the other side. So when it gets on the other side, I get F is equal to FSA, which is mu S M A times G. And then I get minus the tension, which we just learned was mu S MAG. So mu S MAG is there. And that'll be a plus now because it's on this side. And then over here, I've got minus MBG, or excuse me, minus FSB. Well, that's with the normal force that we found for the 5 kilogram object, where we found the normal force was MA times MG. So that's going to be plus mu S MA plus MB, all that times G. So what you see is I got a mu SMA, I got a mu SMA, I got a mu SMA. So finally I can say that F minimum, the minimum force you can apply, or I can say it this way, it's got to be greater than or equal to mu S times 3 times MA plus MB times G. Sorry about that, all looking so scratchy there. But that should be the result. We can plug that in. This is 3 times 3, that'd be 9, plus 5, that'd be 14. 14 times 0.6. Whoa, no, put my elbow on a key. So this is 14 times 0.6, that'd be 1.4 times 6, that's 8.4. And then 8.4 times 9.8. Might as well be 8.4 times 10, that'd be 84. And then minus 0.8, 0.2, yeah, I'll just do the math. Anyways, so I get 14 times 0.6 times 9.8, and I get 82.32. So that's actually the answer. This is it symbolically. And this is it numerically. Okay. This, by the way, is number 31 from chapter 4. No, chapter 5. So you can look that up in your book as well. I don't think I even changed the numbers. I think I kept the numbers the same. Now, part B, all I'm going to do is change this force to, instead of 82.3, I'm going to change that force to 82.3 times 1.2. So let's do that part real quick. Anybody have any questions on this before we go to part B? Anybody want me to rehash it, explain exactly what we did or anything? Okay. So it looks like you are getting it. That's a good thing. Hopefully, that's what's going on. Okay. So now part B, I'm going to pull this down where you can still see what's going on. So actually, let me use the black pen. So for part B, F is going to be equal to 1.20 times 82.32 newtons. That's carrying the extra digit there. So 1.2 times 82.32 gives me 98.8 newtons. So now what I'm going to do is I'm going to take my result that I got here, but I'm going to leave the M's and A's together. So I actually have a force equation with everything in it. So if I take equation 2, which was T minus Fs is equal to M sub A times A, and I take equation 3, which was, or excuse me, equation 4, which was negative T. I keep leaning my thing on that. Hold on. Okay. So there's 4. So negative T is going to be there. I'm going to say plus F. So plus 98.78 newtons minus FSA. So we know it's going to be kinetic friction now because it's moving. So I'm going to say, in this case, it's going to be minus FKA. So it'll be mu kinetic, which is 0.20, times the normal force, which was just the 3.00 kilograms times 9.80 meters per second every second. I've got minus the tension. I've got minus 98.7. This is also going to be the exact same thing, which is 0.20, 3.00 kilograms times 9.80 meters per second every second. That takes care of that one, and that one. Now I got to do this one, which is minus 0.20 times 14.0, because that's 3 plus 5. That's 8.00 kilograms for that one. And that's equal to MB times A. So I add those two equations. You see the tension cancels out. I'm going to get 98.78 newtons minus, let's do what 0.2 is. So 0.2 times 3 times 9.8 is 5.88 newtons minus 0.2 times 8 times 9.8. Left off the 9.8 meters per second every second. That's equal to 15.68 newtons. Again, I'm carrying an extra digit in these places right here. Maybe not for that one, actually. But the left-hand side, when I add these two, becomes MA plus MB. So that's equal to 8.00 kilograms times A. So I can see A is going to be equal to 98.78 minus 5.88 minus 15.68. That gives me 72.22 or 77.224 newtons divided by 8.00 kilograms. And remember, a newton is a kilogram meter per second per second. So that's just going to give me exactly the units I want. So I'm going to divide that figure by 8, and that's 9.653. That's a couple extra digits, meters per second every second. So that's all you had to do to finish up that. That's actually a big acceleration. Almost G. So any questions on that? Try to make sure I didn't leave any terms off. I had an F, which is there. I had a minus T, which is there. I had a minus the static friction force, which becomes kinetic friction force on A. So that'd be 0.2 times 3 times 9.8. And then minus the friction force on B, which would be 0.2 times the total mass times 9.8. So that's there. And then, of course, when I added these two sides, that's just MA times A plus MB times A. So that's just MA plus MB in parentheses times A. So that's how I got 8 kilograms times that, 8.00 kilograms. That makes sense. All right. Anybody have any questions on that? Nada? All right. So let me show you something kind of neat. There's two other things we need to learn about in this chapter. I've sort of done the main part, which is the friction, but there's also motion in a circle, which means we need to understand what kind of force is necessary to keep something in a circle. And I also need to cover the idea of a drag force. In other words, a force of air resistance when an object is falling. Okay. So the first thing I'm going to do is I'm going to do the motion in a circle. And this is actually a pretty important problem. It's kind of one of those things where I have a story where someone didn't understand physics and it resulted in a tragedy. Okay. So for instance, it was probably a good 10, maybe 20 years ago, I was watching a 60 Minutes episode, and these, you know, I think 6 or 7 friends were going out to all these cool parks out west, you know, like Grand Teton and some of those parks at Moab and Utah and stuff like that. And what they do is they just attach a big cable or a big rope to some cliff edge or something, and then jump off and then swing back and forth. And you've seen people doing that all over YouTube and stuff like that, TikToks. It really looks fun. So this one guy had an idea. Hey, let's do that. And so he went around, they were doing that all together, and he said, okay, let's do the big one. Let's go to the Golden Gate Bridge. And you might not understand this, but the Golden Gate Bridge is like so high that people use that to commit suicide. It's literally so high that you die if you hit the water. So it's not a something that you can just, you know, jump off of and maybe get a little hurt foot or something. So this guy goes and he weighs all of his friends, and his friends come up to like a weight of 1,500, and he goes into a store, say Home Depot or something, and finds this cable that has a 3,000 pound limit. He's like, oh, great. They weigh 2,000. I got a 3,000 pound. That's literally like 50% overkill. So we're safe. So he attaches the cable, he attaches it to each of their harnesses, and then they all decide they're going to jump off. And they jump off the Golden Gate Bridge, and it starts to swing, and it gets down about this angle, say, and the cable busts. And like one person hit a boat. I think one person actually died. One person was a quadriplegic for the rest of their life. And another one got some pretty bad injuries and all this stuff. And the guy was actually jailed for neglect or something like that, some kind of, you know, crime where he should have known better, basically. But the problem was he didn't know better. And the deal is the cable doesn't have to just hold your weight when you're on a swing. The cable has to hold your weight, plus it has to provide a force that we call a centripetal, that's CENTRIPETAL. So that means center seeking force. You've got to supply that for it to stay in a circle. So what I'm going to do is I'm going to tell you, I'm going to compute and get you to help me compute what the acceleration is that's required to maintain that circle. So I'm going to advise you that the radius, or excuse me, the vector r is a vector of position for a particular object. So I'm going to turn the document cam back on, and we're going to say this vector r points from the origin to the location of a particular object that happens to be, I'm going to convince you, going in a circle. I'm going to say, in fact, that r is equal to r cosine omega t I hat plus r sine omega t j hat. And I'm going to tell you that omega is defined to be 2 pi times the frequency, which would mean the frequency is like the number of times the thing makes a complete circle every second. But you can also write it as 2 pi over the period, which is the time required for it to complete one trip around. Okay. So with that, I can go ahead and think about this. And what I'm going to do is I'm going to make a plot of t versus x versus y. Okay. And I'm going to say r is equal to, I'm going to say the period is going to be 4 seconds. So let t equal So what we have is r is equal to r times cosine. Notice with t being 4, that'd be pi over 2 t I hat plus r sine pi over t, or over 2t times j hat. Okay, so at t equals 0 seconds, what is this figure? T is 0, so the cosine of 0 is
1.
1. So this is going to be just 1 times r. And of course, sine of 0 is just 0, so that's going to be there. So I'm going to imagine this is my x-axis. This is my y-axis. And let's say this is the radius r. So this is t equals 0 seconds right there. Let's try 1/2 a second. So if I put t equals 1/2, I end up getting pi over 4. And remember, cosine looks like this. This is pi. This is pi over 2. And of course, pi over 4 would be root 2 over 2, which is, you can just call it, yeah, root 2 over 2 r. And of course, the sine is the same for that one as well. So that's square root 2 over 2 times r. And that is exactly what you expect for the particle being right there at t equals 0.5 seconds. What about t equals 1 second? So now I have t equals 1. That means it's cosine of pi over 2. And what is the cosine of pi over 2? 0. And what is the sine of pi over 2? So for recollection, we know that the sine looks like this. This is pi. This is pi over 2. So we can see that's just 1. So that's going to be r. So this is t equal 1 second. T equals 2. We get 2 pi over 2, which is just pi. Cosine of pi is in fact -1, so it's going to be negative r. And sine of pi is just going to be 0, so that's 0. So this is t equal 2 seconds. And 3 seconds, I get 3 pi over 2, which is this value right here, which is 0. And it's this value here, which is negative r, -1, so it becomes negative r. So in fact, it's here at t equal 3 seconds. And then at t equal 4 seconds, you can see it's 4 over 2, which would just be 2 pi. And of course, cosine of 2 pi is 1, sine of 2 pi is 0. So I get r and 0 again. So it's also back here at 4 seconds. So I think you can see that that is, in fact, the vector position of an object going in a circle. And in fact, it appears to be a circle of radius r going in a counterclockwise direction. And the velocity vectors look like they'll be that, which we'll see in a second. Okay. So now let's use that to calculate the velocity. So we know velocity is equal to dr dt. That's what we learned in our second chapter, right? So I'm going to treat it as this using the omega t, not applying a specific omega. So the derivative of r with respect to t, remember I hats, j hats, and k hats are just constants. They go in and out of derivatives and integrals. So if you're in Cartesian coordinates, life is great. The derivative of cosine is negative sine. So I'm going to get negative r times the sine of omega t. Then I got to take the derivative of omega t with respect to time. That's just omega. So I get negative omega sine omega t I hat. Similarly, the derivative of sine is just cosine. So I get r omega cosine omega t j hat. You can probably figure out that at t equals 0, obviously, this is going to have no component at all. So there is no x component. This is positive, so it is going to have a positive component. And in fact, its magnitude is going to be r times omega. So you get this v right here is r times omega, because that's all that's left. Isn't that cool? And we can see it only has one component, so it is pointing in the direction I suggested. Each of the vectors' velocities are in fact perpendicular to the radial line, but it's also tangential to the curve. So that's something that's helpful. Now I'm going to calculate the acceleration, which is, you can either write it as d2r over dt squared, r, the more normal, easier way is just dv over dt. So the derivative of sine is cosine. So that negative stays there. I'm going to say omega squared r cosine omega t I hat. And the derivative of cosine is negative. So now I'm going to say negative omega squared r sine omega t, which I think you can tell looks just like negative omega squared times the r vector. So this vector, in fact, must point that way, and that way, and that way, and that way, and that way. And its magnitude, if you look at it, should be omega squared r. So A is equal to omega squared r is the magnitude. You can do that by using the Pythagorean theorem. You're going to get omega to the 4th r squared cosine squared plus omega to the 4th r squared sine squared. So omega to the 4th r squared is going to appear in both terms. You can factor it out. You get sine squared plus cosine squared. That's just equal to 1. You take the square root of all of it, and you end up getting that the magnitude of A is just omega squared times r. Now that's all well and good, but check this out. We wrote A is equal to omega squared r. Well, I can also write that as I can take this r and I can use this form for omega. So I'll get 2 pi r over t. That takes care of that r. And now I still got an omega, which is 2 pi over t. But check this out. I can write that as r up here, and then I'll multiply it by 1 over r. Because if you multiply by r and then divide by r, as long as r is not 0, everything's fine. Hey, buddy. What you doing? So does anybody recognize what this formula is? 2 pi r. Anyone? Anyone recognize it? It's the distance around here, right? Circumference. And the period, t, is the time it takes to go around there. So in fact, this is velocity, isn't it? So what you see is the acceleration actually has a magnitude that's equal to v squared over r. That's v, and then 1 over r is left there. That is, in fact, our centripetal acceleration. So I'll say A centripetal is equal to v squared over r. That's a general result. We can use it. And in fact, that's how much, if you multiply that by the mass of the people that were swinging on that cable, that's how much they exceeded just their weight. Because the cable had to be strong enough to support mg, but it also had to support mv squared over r. So they needed not only the, if they weighed 1,500 or if they weighed 2,000, they needed not only 2,000 pounds, but they also needed mv squared over r. So any questions on that? Okay, so the typical problem that we solve now is one where you're basically going to do a banking on a curve. So I'm going to do that next. But I had a visitor to come to see me. I figured y'all might like to see my little buddy. Say hi.
Oh, hi.
Say hi, Cosmo. He came to see me. He's my little chihuahua. Does he look like Gizmo from Gremlins? Or an Ewok, maybe? All right, let me put him back over here. Here you go, buddy. Oh, sorry, buddy. Otherwise, he won't be able to find his spot and he'll have an accident. So let's consider a problem where we use that. Now, what we've basically learned is that in order for something to go in a circle, let's say like this, then that object has to have a centripetal acceleration pointing towards the center of the circle, and in fact, in the same plane that it's going in a circle in. So that's key. Now let's take a particular scenario. I'm going to draw a inclined curve, or actually, I just guess I'll just turn my camera off for some reason because I'm a goober. So I'm going to, come on now. There it goes again. I like how I have to focus it every time. That makes it extra special. And it's such a delay that I keep turning it back off because I think I didn't hit it. Waiting. Okay. That picture doesn't look too bad. We'll see how it looks when I start actually writing. So now let's imagine that we have an inclined plane for a car. What I want to know is what angle theta will allow a turn of radius r. Oh, I misspelled radius r at speed v with no friction. So that's our problem. So what I have here is a little car. There's the wheel or tire. There's the other tire. There's the bumper. There's the grill of the car, the cab of the car, say like that. And in fact, the forces acting on it are the mass of the car with no friction if the car has a mass m. So I just made the mass m what we're doing here. So this will be mg, and it also has a normal force acting this way, F normal. Okay, so I'm going to draw a free body diagram again. And often, since it's an incline, we might want to write a tilted coordinate system, but in this case, we do not. The good news is I'm showing you sort of all the cases. So, you know, hey, if Mr. Younger's asking me to solve for a radius of curvature or for an angle of incline to keep a car sliding off the thing, then I'm going to use a non-tilted coordinate system. But if I'm solving an incline plane problem, I'm probably going to use a incline coordinate system. So what I have here is, I can imagine this is the angle theta right here. That means this angle is also theta. And then this angle right here would be 90 minus theta. So this angle has to be theta. But that's my normal force right there. Okay. Now in this coordinate system, I do have a weight pointing downward, which is mg. And in principle, we might actually have a friction force F static going that way, but I'm going to try to do it with no friction. But I just want to show you which way. Oh, actually, excuse me. I drew that wrong. Remember, the friction force would be along the surface. So I'd actually have to draw that black because it's not along one of the axes. And it'd be F sub S like that. Okay. Now I have to break this up into components parallel and so on and so forth. So what I get is a vertical positive Y component, if you will, for the normal force. And that's F in cosine theta. And then I get a positive X component. That's F in sine theta for the normal force. So for the Y component, I get Fn cosine theta minus mg is equal to 0. Again, I'm ignoring the friction, so I'm going to say that's 0 right now. Otherwise, I have to find components of it. Okay. But if you wanted to work it out with friction, that's where the friction would go, and you'd have to break this up into an X component and Y component. So that's partly why I put it there. So we're saying right now, no friction. So what that gives me is that the normal force is in fact equal to mg over cosine theta. Don't know that that's necessarily helpful, but anyways, that's something to keep in mind when you do a problem. I said when you do a problem that has friction. Now, I make me laugh. That's the important thing. Now, what we have to realize here is that there is, in fact, an acceleration. The acceleration has to be the centripetal acceleration, which is v squared over r, or it's not going to be able to make the turn. So now I'm going to take the x equation, and I see that the only force acting in the x direction is Fn sine theta, and that's got to equal m times v squared over r, right? Well, luckily, combine 1 and 2, and we get Fn is being replaced by mg over cosine theta times the sine of theta is equal to m v squared over r. I think you can see immediately that the m's cancel out, and we end up getting, lo and behold, another tangent function. We get tangent theta is equal to v squared over gr. So the answer is clearly theta equals the inverse tangent of v squared over gr. Now, I suspect it's really easy if you've done this, if you derive this yourself, it's going to be really easy for you to remember what that formula is. It's literally the only way v, g, and r can go together for vg to cancel out g and r. Because remember, the units of the trig function have no units. So g times r must have units of v squared. Okay. But that's the angle of the incline. Any questions on that? All right, we're supposed to go to 720. I didn't give you a break this time. So I think what I'm going to do is go ahead and solve the problem of a drag force. Okay, so let's start now. I'm going to draw a body. Anybody have any questions on that last one we just did? Okay, so what I'm going to do is I'm going to assume this is the positive x direction. I'm going to assume there's a body of mass m, and therefore there is a force mg acting downward. That's its weight. That's gravity pulling on it. Okay. But we're going to say there's also a drag force on it. Okay. Well, it turns out F drag is easily either proportional to V or proportional to V squared. We're going to do this one. Okay. Now, there's actually an equation you can use for it. In fact, my wife is a cardiac sonographer and they use the equation for that. But basically, the coefficients that go between it to make it an equality is a number that's basically the viscosity of the air, or if you're going through a liquid, it's the viscosity of that liquid, the cross-sectional area, and then some other factor you can put in there just for aerodynamicness or something like that. So basically, what we're going to do is we're going to say this is equal to B times V. So the summation forces in the y direction, or excuse me, in the x direction equals mass times acceleration in the x direction, gives us something pretty straightforward. It's going to give us mg minus bv is equal to m dv dt. Notice I used, instead of using just plain A, I used A as dv dt. This is what's called a separable differential equation. And what I'm going to do first is I'm going to divide both sides by m. And now what I get is g minus bv, b over m times v, is equal to dv dt. So it's separable because I can take this whole thing, it's only a function of v, and I can divide both sides of the equation by it, and then I get g minus b over m times v is equal to dt. I'm going to integrate this from t equals 0 to sometime t, and I'm going to integrate this from v0 equals 0 to v as a function of time. To do that, I'm going to let u equal g minus b over m times v, then du is equal to negative b over m times dv, or dv is equal to negative m over b times du, which I like better because I can just throw that in there. Okay. So now what I'm going to get is the integral of negative m over b of du over u, and that's from v0 equals 0 to the v of t, just to remind me that it's not u that I'm dealing with. This one just integrates to t. So we know the integral of du over u is just ln of u. So I'm going to multiply both sides by negative b over m. That's going to get rid of that. And I'm just going to have the ln of g minus b over n times v of t over just g. Because notice when I take the ln, I'm going to first do this one, which is g minus b over m times v of t. And then I'm going to say minus the ln of just plain g, because the v is going to be 0 there. But when you subtract one ln from another, that's the same thing as dividing by the arguments. So I got that. And this is going to be equal to negative b over m times t. In math, we're going to play it fast and loose. So I'm going to imagine raising e to the left-hand side power and simultaneously raising e to the right-hand side power. When I do that, I get g minus b over m times v of t over g is equal to e to the negative b over m times t. I can now pull the g over here, and I'll get g minus b over m v of t is equal to g times e to the negative b over m times t. Now I can pull this whole term to that side and pull this whole term to that side and then flip them. So that's ultimately going to give me v of t is equal to, it's going to become positive now, of course, but it's going to be b m over b times 1 minus e to the negative b over m times t. So as you might have expected, this sort of is an asymptotic plot. In other words, if I plotted velocity as a function of time, I would basically get b equals mg for this, or v equals mg over b. So v equals mg over b. And this velocity is going to approach that like an asymptote. So that's actually what motion with a drag force looks like. Any questions on that?
Can you just skip it there for a second?
Yeah, no problem. I think your book does list that equation as a numbered equation, which means if you do this, you're not going to solve that differential equation. You're just going to use the result. So solving differential equations is a little bit beyond what we're asking of you. All right, you folks are free to go. I'll wait for the last person to leave. Don't forget, you got a test due Monday evening. That's a online test. You're allowed to use open notes, open book, open Google searches, but your time is limited. And I still give you 3 attempts, and I only take your highest one. Okay. What you're not allowed to do is ask someone for help, or text someone, or talk to someone on the phone to get help. Or if someone's already taken it and they create a website or a page or something like that, you can't read any of those things. So anything created after today's date on the internet, you can't use. But other than that, you can use everything else. Do not go over the time, because I take off 10 points per minute and I count minutes like cell phones do. So 0 to 60 seconds is 10 points off, or excuse me, 1 second to 10 seconds is 10 point, or to 60 seconds is 10 points off. And at 61 seconds, it becomes 20 points off. Oh, the class is, oh God, I just remember that crap. I was thinking the class was ending at 7:20, but yeah, that's not right. That's good, because that gives me time enough to do one more problem. So don't leave yet, everybody. Thank you. I was just remembering my class this morning, which is supposed to be over at 20 after. So that's why I was screwing up on that. Does everybody see how this works out? I do recommend you go in and take sample values of M, G, and B, and then plot it in Desmos or plot it in your calculator and see how you can make different things happen. But I think you can see as E goes to, or excuse me, as T for time goes to infinity, this is 1 over e to the infinity. So that becomes 0. So you end up just getting mg over b. That's why I knew the asymptote was at mg over b. But I'm so glad I remember, because there's another problem I wanted to work, and I was bummed out I didn't get to work it for you. So anybody have any questions on this before I go on to the next thing? Okay. So thank y'all for not leaving yet. I'm glad y'all are cool enough to realize I'm an idiot before I did. But anyways, here we go. So I've got this neat problem. One of my professors showed it to me when I was an undergraduate. And he said, this is a good problem. If you can do this, you can do anything. It's like, okay, so I'm going to give it to you and I'm going to help you guys see what it is, but it's kind of tricky. So what we're going to have is an inclined plane like this. And its angle is theta. And I'm going to have an upside down inclined plane whose angle is also theta. And it's got these cool little frictionless wheels on it. And then on top of that is a scale. And then on top of that is a fat physics instructor whose mass is big friggin' M. Okay. So, and I'm supposed to be level and plumb there. So you ignore the fact that I'm leaning a little bit. But anyways, a free body diagram of this, for instance, if this is the x-axis and this is the y-axis, is in fact, we got F scale pointing up. That's the force the scale is applying to me. And then I got mg pointing down. But here's the kicker. My acceleration is also downward. Okay, so this is not a reference frame that's sitting still. This is an accelerating reference frame. But when I solve for F scale, that will give me what my apparent weight is. My real weight should be m times g, but my apparent weight is what the scale weighs. And what I want to know is, what is my apparent weight? And really that just means F scale. Okay, so I didn't solve one of those elevator problems. I saved it to do this. And you guys can now hopefully do the elevator problem. If you put a scale like this in an elevator, you're still going to have a free body diagram involving F scale and weight. And the elevator will be either accelerating downward or accelerating upward. Okay, so you can see that that's going to change your weight. And you've probably ridden in an elevator before. When you first take off on the upward direction, your legs feel like you got a little bit heavier. And then when they slow down at the top of the vertical upward motion, it feels like you got a little lighter. In fact, I actually normally do this because I'm still 12. I jump up in the air and see how high I can get. And I get my daughters to do it. And one time we even got the elevator at my old school jammed. So that was kind of cool. But anyways, that's what we're going to do. So anyways, you can test this kind of stuff with everyday life. And the beauty of this is when it's done, I can check special cases of theta. And if they make sense, then I've got more confidence that it's right. Okay. So I'm going to take right here and say the y direction is going to give me F scale, which I'll call just Fs, minus mg is equal to, now this is pointing in the downward direction. So I'm going to say it's minus m times a. Okay, that way a will have a positive magnitude. I put the negative there just to show that it's going in the negative direction. So that's one equation I'm going to use. Now, let's say for the sake of argument that the mass of the incline and the scale and everything is just lowercase m. Okay. Now, in this case, what I'm going to do is draw a coordinate system that is x prime, y prime. And the forces acting on that little mass m for that case is in fact this force mg and this force F normal. Okay, so now I realize that this has the mg has a negative y component. So I'll draw that red like that. This is going to be the angle theta as we learned earlier, but it has a positive x component. And in fact, I see that this is mg sine theta. And the reason I know that is this red one's actually touching the angle, so it has to be adjacent, and cosine is associated with adjacent. So I'll say mg cosine theta is this guy. So that gives me that the normal force minus mg cosine theta is equal to 0. That's for the y prime direction. So Fn is just equal to mg cosine theta, which doesn't really help me much, but I just did it for completeness. Now the x component gives me some cool stuff though. So x gives me that mg sine theta is just equal to ma. Because that's the only force acting that way. And that's, of course, the x prime direction. And I'm going to call this equation 3. Okay. So what 3 gives me, 3 implies that A is equal to, notice the masses cancel out, it's just equal to g sine theta. But that's kind of weird because that's not the same A as this one. In fact, I probably should subscript it sub B or something like that to make sure you know it's not the same. Notice that's the acceleration down the incline. I need the vertical acceleration. So yet I need to yet draw another diagram that is in my coordinate system, which is x and y, but has the A in the coordinate system that we just worked out. We found that A was going this way, which of course means that angle theta right there. So it also means this angle is theta right here. I have A, B is equal to g sine theta right there, and that's that one. Okay. Now that makes a positive x component. That's A sub x is equal to A sub b cosine theta. And it makes a negative y component. And that's A sub y is equal to A sub b times sine theta. Okay. Well, that's all I need. I really don't need any information about the x component of acceleration. I need to solve that. So now I'm going to take this, which I'm going to call equation 4. I'm going to take 4 and plug it into 1. And from that, I will get F scale minus mg is equal to m. Now A, you can see, is going to be a b sine theta, but AB is in fact equal to g sine theta. So I get m times g times sine squared theta. So I now get Fs minus mg is equal to mg sine squared theta. Or finally, I can say the force on the scale is equal to mg times 1 minus sine squared theta. Or F scale is equal to mg cosine squared theta. Isn't that cool? It's one of the rare times you get a trig function squared in a term, but this is where it's coming from. And now, when I talk about the special angles, can anybody tell me what my weight would be at a specific angle theta? Tell me in other words, tell me a theta where you happen to know what my apparent weight would be. Do y'all know anything about apparent weight? Like, for instance, how does apparent weight become your actual weight? Can you think of a theta that would make your apparent weight equal to your actual weight?
I was thinking theta equals 0, but I could be wrong.
Very
I'm
good.
just oh, is that it?
Yeah, that's it.
Okay.
So theta equals 0, you expect that the weight of the scale is just everyday scale, right? It should just be m times g. Well, let's check. So according to this, F scale would equal m times g times the cosine of 0 quantity squared. Now I wrote it out here instead of up to there. Everybody knows what the cosine of 0 is. So it's just mg. And that's right. That's what we expect, right? If the thing's not actually accelerating, we're not going to expect my weight to change. What about, do y'all know what your weight is when you're in free fall?
Isn't it just mg, or are you weightless?
It's weightless. In fact, that's the reason the astronauts in the International Space Station or in the shuttle, whenever they were in orbit, they were experiencing weightlessness, not because gravity's not pulling on them. You know, gravity holds the moon to the Earth, and the moon is way farther away than they do their orbits normally. So, in fact, they're weightless because they're in free fall. That's the same reason why those negative G turns in Apollo's chariot feel funny, like feels like you're going to lift out of the seat. You get kind of light on your stomach, sort of butterfly. Or if someone goes too fast over a railroad hump in the road, you feel your stomach kind of come up. That's weightlessness. So theta equals 90 degrees. You expect the weight of the scale, or excuse me, the force of the scale. I should have said that with the other one too. Let me change that to F instead of. So this is F scale. So you expect F scale to be equal to 0. So let's check that. So when I check that, just like I did before, I get F scale is equal to mg times cosine squared 90 degrees. Anybody recall what the cosine of 90 is?
0.
0. So in fact, we get 0 and we get mg. So this is another critical thing to learn about physics is when you're doing it, there's certain things you know, and you can examine those special cases and see if they make sense with the answer that you get. If they don't make sense with the answer that you get, then you need to either check the logic that gave you that idea that the answer was going to be something, or you've made a mistake on your problem. So that's a whole nother thing that's super helpful, I think, to people, is just letting them realize that, hey, these results that you get when you write them in symbolic form, like I have here with, you know, theta and m and g, instead of actually filling in numbers, you can use those for an infinity of problems. And since you can use them for an infinity of problems, you can also consider the very special cases of those problems. Like with the Atwood machine on an incline, you should expect the result for an Atwood machine that's not on an incline in the case of theta equals 90 degrees. So that's another, you know, special value you can check. So does anybody have any questions on that? All right. Well, now I'm really going to let you go, and I'm letting you go 18 minutes early. Okay, not 10, but I appreciated you sticking around for, even though I told you you could leave way before time, because that was just me having an Alzheimer's moment. So it's not funny to laugh at. That's one of my big 3 things that I'm a hypochondriac about. My grandmother had Alzheimer's, so I'm convinced I'm going to do it. Oh God, my hair's getting even less. Anyways, so anyways, you folks are free to go. I will wait for the last person to leave. Get your homework done. I did move the chapter 5 homework to Sunday the 19th, and chapter 6, assuming we're able to cover it all Wednesday, or I'm content with how much we cover on Wednesday, then it'll just be due by Sunday the 19th as well. And the test will be due on the 20th. We may or may not be behind on where test 3 is coming, but I'm not worried about that. So we'll deal with that later. I'll talk to you about it next class, but you guys are free to go.
I had a question on the syllabus. There were 2 syllabus, I guess, that were out. One that was saying the exams were worth 50%, and another one said the exams were 10%.
Ooh.
So I just wanted to know.
There must be a typo in the 10% one. I think this year, because most of our tests are going to be face-to-face instead of online. I think what's left there is I had a 10% test for all the online tests. But yeah, you can ignore that. I don't know how it got there, but there should be one syllabus that just says syllabus spring 2022 or summer 2022. But then another one will have a date on the end. That's the most recent one. And that should be the correct one. But now I'm going to have to go check in there and see if I did make that mistake and correct it. But yeah, the actual tests are worth, if I remember correctly, 50%. Definitely not 10%. I know they're not 10%, but I'll check on that again and let you guys know.
Yeah, I think there's 3 out in total. I know there's definitely 2, but I think there may be 3, all saying a different thing. So I appreciate the clarification.
Yeah, thank you very much. Make sure the one you're looking at has a SU 22 somewhere in the document, and maybe even on the name of the document, but specifically in the document. Because if there's old ones, if I have 3, that's almost certainly a case where it's from a previous semester. So it should have something on the document saying it's for spring or fall or something like that. But yes, I will check that, and thank you for keeping me abreast of that.
Okay, thank you so much. You have a good rest of your evening, Professor.
You too, Courtney. Have a good one.
Thank you.
Anybody else? Man, I got like 4 Josiahs this semester. Cool. Josiah, Patterson, or Upperman, do y'all have any questions? All right. Well, I'm going to go ahead and assume you guys are not here. Josiah Upperman, you don't have anything? All right. Well, have a good day, guys.